Hey everyone, hope everyone's still keeping healthy and like staying safe. So welcome back to this week's lecture videos. So what we're going to do this week is start discussing chapter 7. We'll start going through material in chapter 7. And for tomorrow's videos, I'm going to make a bunch of short videos. I think 30 minutes each, roughly. That's my target, because I'm trying to break it up and then discuss things in like small bits. Okay, so to start off, I do want to go ahead review some of the stuff that we did. Very general overview of what have we done in the past week, or what is it that we learned in the past week. So what we did last week was we talked about chapter 10. Okay, this was on halogenation. Now, I do want to mention that we didn't discuss all of chapter 10. I think we went up to 10.6 or something like that. That's the section that we went up to. So that is where we talked about, like, one of the last things that we discussed in one of the problem sessions, where we talked about halogenations that result in the formation of a chiral center. Okay, so that is how far you want to go in chapter 10. There's more stuff in chapter 10 that we will come back to later when we're in chapter 8. So we're going to come back there. So we talked about halogenation of alkanes. Okay, now when we talk about alkanes, I think alkanes is pretty broad. So what I want you to get, I guess, in some sense, get straight, when you think about these topics, is what is an alkane? So ask yourselves, what is an alkane? How do you understand an alkane? Okay, what is it that comes to mind when you think about an alkane? And you might want to think about a compound which has carbons and hydrogens. It has only single bonds in it, no double bonds. And so so those are all general terms. Now, if you were to talk something more organic-y, like use organic language, I think when we refer to alkanes, we're talking about carbons that are sp3 hybridized. Okay, these are carbons that are sp3 hybridized and have hydrogens on them. This is what we talked about. So if you have a molecule, okay, and let me draw a molecule here. Let's say that. Now, is this molecule an alkane, the molecule as a whole? No, it's not, because it has some double bonds in it. Okay, so that is an alkene part of it. In fact, this is a ring, so it's an aromatic compound. But if you look at this part of the molecule, which is this chain, these carbons, they are all sp3 hybridized, and they have hydrogens on them. Okay, so whatever we learned in chapter 10, that will apply to this part of the molecule, because these carbons are sp3 hybridized and they have hydrogens on them. It does not apply to this part of the molecule, but it would apply to that part of the molecule. So that's something that I want you to remember as you go through problems and you look at questions and things like that. So if you see a molecule with some double bonds on it or double bonds in it, do not think that anything that I learned in chapter 10 does not apply to this molecule, because this is not an alkane. Yes, this part of the molecule is not an alkane, it's an aromatic, but that chain is an alkane, or is of alkane nature, okay, because these are carbons that are sp3 hybridized. So please remember that okay, so that is what we talked about. And essentially what we did is, in chapter 10, we looked at free radical chlorination. We talked about free radical bromination. Okay, so that is what we covered, chlorination and bromination. So free radical chlorination and bromination. Okay, these are the two reactions that we looked at. They're useful because what they do is they convert alkanes. Okay, these reactions convert alkanes into alkyl halides. Okay, so both of these reactions, they do that. They convert alkanes into alkyl halides. Now, the other important thing that we learned is that bromination is a selective reaction. Okay, it will give you one major product. So it is selective. It will give the major product from the most stable radical possible. Okay, that is where your major product comes from. If you have a choice between primary, secondary, and tertiary radicals are the most stable of those three, and so your product is going to come from the tertiary carbon. If you have tertiary and allelic, and you might want to go to chapter 6, the bond dissociation enthalpy table, and look at some of these, and in chapter 10, look through some of these to identify some of these things. So if you have a brominate, if a tertiary and an allelic position, then the allelic is more stable. Okay, so the product would come from an allelic radical, things like that. So that is where the bromination would happen, but you would get one major product. Okay, so that kind of gives you an overview of what we discussed in chapter 10. So now moving on to chapter 7 from here. So chapter 7 deals with reactions of alkyl halides. Okay, so this is dealing with the reactions of alkyl halides, and we're going to learn two broad category of reactions of alkyl halides. So make a connection, alkyl halides were the products from the free radical halogenation reaction that we saw in chapter 10. So we learned how to convert alkanes into alkyl halides. Now we're going to see what can we do with alkyl halides. What sort of products can you make, or what sort of organic compounds can you make from an alkyl halide now? So you're basically building it up. Alkane to alkyl halide to what now? Okay, that is where we are going. And again, just to make this clear, when we talk about alkyl halides, we're talking about a very specific category of compounds. Okay, we're talking about carbons with halogens attached to them. And again, we're mostly going to see chlorine, bromine, and iodine, not so much of fluorine. Okay, and we will talk about that later, and you will kind of realize why. But we're talking about carbons which have halogens connected to them, but this carbon is also sp3 hybridized. Okay, so it is what you get from, or these are the products from chapter 10. Alkanes giving you alkyl halides. So we're talking about carbons that are sp3 hybridized. That would be the discussion, or those would be the discussion in chapter 7 would be focused on these. We will not, okay, we will not be talking about this. When a halogen is connected to an aromatic, we will not be discussing these. I mean, I will not be bringing these up, and what you have to realize is whatever reactions we learn in this chapter, they do not apply to these molecules. And we will not be discussing molecules like that, let's say. Okay, these are called vinylic. Okay, so when a halogen is directly on a carbon that is sp2 hybridized or on a double bond, then they are called vinylic halides. These are aromatic halides when the halogen is connected to an aromatic ring. So we are not discussing these in this chapter. We will be limiting ourselves to alkyl halides. This is when the halogen is connected to a carbon that's sp3 hybridized. So please remember that for everything that we'll be discussing in chapter 7. We will see, yeah, in fact, you're not going to see any chemistry of both of these in 3140. That comes up in 3150. Okay, the next semester is when you're going to see it. So not this semester. We are focusing everything on this. So before we start discussing the chemistry of alkyl halides, we want to familiarize ourselves with two terms, okay? Nucleophile and electrophile. Now, we've talked about these generally, but I don't know if I've used this name, so I just want to go over it very, very briefly, to kind of update you on what do these terms mean, how do we interpret this, okay? So nucleophile and electrophile. So nucleophiles, these also have another name, which is a Lewis acid. So it's still acid-base chemistry. Sorry. Nucleophile is Lewis base, and electrophile is Lewis acid. Okay. So it's still acid-based stuff, but the definition now changes a little bit. And again, if you think about acids and bases, going back to chapter 3, we've talked about two kinds of acids and bases. We talked about Arrhenius acids and Arrhenius bases. Arrhenius acids donate protons, okay? Arrhenius bases donate hydroxides. So that's like the very basic of acids and bases, HCl versus sodium hydroxide. Then most of our discussion in 3150 was based on Bronsted acid and Bronsted base, okay? A Bronsted acid is a proton donor. A Bronsted base is a proton acceptor. So that's exactly what we looked in chapter 3. We looked at molecules and we kind of evaluated them based on their proton donor or proton acceptor properties. We evaluated their stabilities and things like that. Now, Lewis bases, Lewis acids, Lewis bases are also called nucleophiles. Lewis acids are called electrophiles. Lewis bases and Lewis acids, these definitions are now based on electrons, okay? So a nucleophile, which is a Lewis base, is an electron pair donor. So anything that can, any species which has electrons to spare that it can donate is a Lewis base or a nucleophile. It's an electron pair donor. So for example, molecules that we've already seen, water has a lone pair on it. in fact, generalize this, anything with lone pairs on it, okay? So lone pairs are pi bonds, and then, as usual, negative charges. So pretty much all the electron pairs that we saw in a Bronsted base, because that is how a Bronsted base accepted a proton. It used either lone pairs or negative charges or pi bonds, and they would accept electrons. So any of those, they also qualify for Lewis bases now. So there is some similarity there, okay? So Lewis base is an electron pair donor. So water would be an example. Let's say ammonia would be another example. Hydroxide could be an example. Okay, anything with negative charges, things like that. Or if we have alkene like that. So this is 3 carbons. So this is propene with an alkene double bond. So propene, that would be a Lewis base because it can use its pi bond to donate electrons. Electrophiles or Lewis acids, on the other hand, I think electrophile or Lewis acid. These are electron pair acceptors. Okay, these are electron pair acceptors, so they accept electrons. And if they accept electrons, okay, and kind of notice that the name comes from there. Electro, which stands for electrons, phile means liking, loving. So these love electrons or like electrons, so they accept electrons. Nucleophile is, nucleus stands for nucleus, which is positively charged, so positive loving. So if they love positive charges, they must have electrons on them already. So that's why they're nucleophiles. Okay, so that's where the name kind of originates from. So coming back to electron pair acceptors or electrophiles, these species, if they love electrons, that means they do not have enough electrons on them, because if they already have electrons on them, why would they want more electrons? Okay, so for example, hydroxide, it has a negative charge on it. It has a lot of electrons around it. Why would it want more electrons? The pi bond here has electrons on it already. Why would it want more electrons? Okay, so electron pair acceptors or electrophiles have to be molecules that are somehow lacking electrons. Okay, these lack electrons. These lack electrons. And sometimes it may be very obvious. So for example, a carbocation, let's say, that carbon is positively charged, this carbon here, okay, that tertiary carbon is positively charged. That means it's lacking electrons. That's what the positive charge is saying. And so in that particular case, that carbon would be electrophile. Okay, it would be an electrophile because it is lacking electrons. It would take electrons from something else. Similarly, let's say this. I have a resonance form written down where the oxygen is negative, the carbon is positive. This carbon is lacking electrons, so this would be an electrophile. Now, sometimes there might not be like an obvious positive charge. So think about a molecule like this, Cl. Now, this molecule does not have a positive charge on it. In fact, it does not have a negative charge on it either. Okay, and now we are basically coming close to home. So this is an alkyl halide, the kind of molecules that we will see in chapter 7. This is an alkyl with a halogen attached to it. How is this an electrophile? Okay, going back to chapter 2 when we talked about bond dipoles, remember that In this molecule here, you have a chlorine and a carbon that's connected to each other. This chlorine is electronegative, so it's a del negative, and this carbon that's connected to the chlorine is a del positive. Okay, so it is electrophilic because it is lacking some electrons, because the electrons in this bond, those are pulled more towards the chlorine. Okay, so that would make this carbon electrophilic in nature. Okay, it would give it a del positive. Now the same applies to, okay, for lack of space, let me draw a molecule here like that. This molecule here, you're going to see this chemistry in 3150. Okay, this molecule here again, this carbon is del positive, this oxygen is del negative, because the oxygen is more electronegative than the carbon. So pretty much whenever you have a carbon that's connected to a more electronegative element, that carbon is going to have some del positive on it, and that would make it electrophilic, electrophile-like. Okay, that is what it would become. So that's a discussion on nucleophiles and electrophiles, and for chapter 7 we will be using these terms extensively. We are not going to extensively. Okay, so we're not going to use any other terms. We will refer to molecules as nucleophiles or electrophiles. Now before I end this portion, I do want to mention that we can categorize molecules as strong nucleophiles, weak nucleophiles, and strong electrophiles, weak electrophiles. Now, sometimes it's very obvious and sometimes it's not, okay? So for example, let's say if we compare water with the hydroxide, between these two, which one's going to be the stronger nucleophile? So stronger nucleophile means it is an electron pair donor. And if it is strong, that means it has a higher tendency to donate electrons. So between these two molecules, which one would have a higher tendency to donate electrons? Hydroxide versus the water molecule. Okay. I hope you guessed it right. The hydroxide oxygen has negative charge on it. It has more electrons on it. In fact, the negative charge kind of gives it away. Okay, that should be a stronger nucleophile relative to the water molecule. Okay, so we can say the hydroxide is a strong nucleophile relative to water molecule, which is a weak nucleophile. We can compare water with ammonia. Which one of these two would be a stronger nucleophile? Okay, the nucleophile, the electron pair donor is the oxygen, because this is what has lone pairs. It's the nitrogen has lone pairs. So we're basically comparing oxygen to nitrogen. And what we know is oxygen is more electronegative than nitrogen. So it would want to hold on to its electrons more tightly, or it will hold on to its electrons more tightly. That means it is less willing to give them away or donate those. Whereas nitrogen, being less electronegative compared to oxygen, it is more willing to donate its electrons. So between these two, the water molecule and the ammonia molecule, we can say that nitrogen is a stronger nucleophile. Okay, so we can basically develop some qualitative concepts like this. Coming to electrophiles. Strong electrophiles, weak electrophiles. Again, strong electrophile would have a higher tendency to basically accept electrons, because that is what an electrophile is. It's an electron pair acceptor. Okay, a weak electrophile would not have that strong of a tendency to accept electrons. So if you look at a few of these molecules, let's say carbocation versus the alkyl halide. Okay, which one of these two would have a higher tendency to accept electrons? I would think it's the carbocation, because it has a full positive charge on it. It is actually missing electrons. So that would be a stronger electrophile compared to this carbon in the alkyl halide, which is only a del positive. So it has some del positive or a slight positive nature to it, but it's not like missing its electrons. The electrons are there sharing with the chlorine. The chlorine is just holding on to them. Okay, so again, strong and weak, so we can talk about those things. So we'll end this video right here. So this is just a brief introduction into what's going to come. So we will use these terms, nucleophiles and electrophiles, and in chapter 7 we're going to be talking about alkyl halides, the chemistry of alkyl halides. That means when a carbon has a halogen attached to it, and the carbon must be sp3 hybridized. Okay, hope you like the video. Thank you.